I've created this new channel called Mathematical Physics Class. You know, many of us who are mathematicians or physicists or engineers, uh, they often find it very difficult to deal with mathematical physics problems. I'm not concerned about the persons who are already means either in college or in their early days, because uh, sooner or later they will definitely learn all these things. But I'm concerned about those who are serious about their career, their future career or their present career. People who are already in work, they should start learning the most neglected subjects as soon as possible, uh, because what happens when you start ignoring some stuffs gradually, when you go to higher studies or when you try to apply those stuffs in your practical life, it starts creating problem. So at that time you feel like it would have been had been better if you would have learned such stuffs during your college days. Nevertheless, it's I believe in saying that it's never too late. You can start learning anytime you want, and you can probably use your stuffs uh, as soon as you start. You learn it, and as soon as you can use it. So I believe it's good कि some of you who have not who those people who are not actually into their career, or those people who are not uh, very good in these things, they have a good amount of time before they will go to their real applied field. That can be either mechanical engineering or thermodynamic experts, or physicists or scientists or mathematician. Wherever you go, some of the stuffs in physics and mathematics are uh, very essential in most of the fields. Those guys who are working with fluid mechanics or finite element or things, stuffs like hydraulics or fluid thermodynamics, they also do encounter such stuffs like where you get to deal with partial differential equation or gradient or curl or a mathematical operator that you might actually have ignored during your mathematical physics classes. I'm not saying that mathematical physics is the only thing that is being ignored during our college days, but because it has a lot of physics plus mathematics plus the real life problems are far away from either mathematics or basic physics. So because of this stuffs, most of us do ignore mathematical methods and mathematical physics problems or equations during the college days, and because they ignore such stuffs, it becomes very difficult for them to grasp you know these stuffs during their practical career time. So I'd encourage each of you guys who are new to mathematical physics or who are trying to learn mathematical physics. For example, if you go to Google, and if you try to find out stuffs like, for example, I can show you. If you go here in Google and if you type mathematical physics books or PDF, or let us say if you go to fundamentals of mathematical physics, because you want to start your career with or your knowledge from the basics, because you might have ignored such things during the classes. So you see, nowadays you'll get a lot of Amazon stores and online books in the first place because they do some kind of SEO optimization and stuffs. But if you go to mathematical physics, I know this because I was just searching few hours back. But if you search mathematical physics books, you see here, and you'll find a lot of books and stuffs. All are PDFs, so probably you can download each of them and start, finding your way from which book you should start with. For example, if you are quite new and if you choose this book, let's say the funky mathematical physics concepts, and if you start using this book, as the name says, it's a really funky book. It's good. It's really good, one of its kind book, the anti-textbook it says, because it's not nothing about. It has nothing about how to begin mathematical physics classes, but you see the stuff. It has stuffs like why hyperbolic. What's hyperbolic about hyperbolic sign means. If you go there, you'll find why hyperbolic functions are called hyperbolic, but you don't know what is hyperbolic, or if you don't know why to use hyperbolic functions, then these stuffs have no use. So I'd rather suggest you to start from a fundamental book, and in this complete channel I'll try to help you, guide you through your mathematical physics learning. I'll take a basic mathematical physics book and start from the beginning, not from the beginning, actual beginning, but from the place where I feel that most of us should start learning from there, because it's quite a bit confusing that from where mathematical physics starts. It has equations starting from algebra to kinematics to scalars and vectors, tensor, Fourier transform, and many of those things. And I'm not sure what the textbooks guide us to do, but we can start from any textbook, and gradually as I progress with the channel and I make a couple of videos, and you guys, if I find people interested in learning mathematical physics, I can probably go through a lot of books which I have kept from which I have downloaded and purchased from time to time and kept with me. I can probably go through those books, and I can solve the problems. I can show you how the stuffs work in mathematical physics. I can teach you the mathematical operators, equations, Gaussian theorems, and whatever it is in the mathematical physics class. And I would say I'll not be limited to just mathematical physics. Gradually, with time, probably we'll discuss a bit of thermodynamics, optics, electromechanical theory, electrodynamics, and all such stuffs. But for now, I'm starting with mathematical physics because when I started my career about 10 years back, after my graduation, of course, in physics, initially I started my career with a company or an organization who was experts in electromagnetic theory. So I tried to learn electromagnetics, but as I progressed in learning electromagnetics, I found that there are mathematical equations that I need to understand. For a time being, I tried to learn mechanical theories because I had to work as a mechanical engineer for some time, and there also I found stress tensors and vectors and all such mathematical stuffs. During my tenure in cryogenics and vacuum related applications, I found a lot of mathematical stuffs. So I believe in all my career I have seen mathematics everywhere, either it is engineering or physics or science, any domain of science. You'll find such basic mathematics everywhere. So I feel that if you learn mathematical physics, you can probably if you go to any textbook and you start reading it, you'll get 30-40% of it easily in the first go. But if you know the mathematics behind everything, and if you can use your hand to calculate some of the basic calculations in any domain, probably you will grasp about 70-80% of any textbook. So I feel that if you are in a science domain, science or engineering domain, you should learn mathematical physics to its best. In my 10 years of actual career, I have learned it the hard way, and gradually after some time I realized that I cannot go beyond a certain point in my career if I do not learn stuffs. And if I don't learn the stuffs, I can use it for different fields where my competitors or my peers or my batchmates, they might not use such algorithms, and because of that I might grow faster than others. It's quite a bit of personal stuff, but yeah, it's true for everyone's career. They want to grow faster compared to their peers, and there I found that the only way to grow faster than others is to learn, or is to invest more time than others. Because if you are better than someone, you cannot be 2000% better than someone. You can only be 30-40% or 10% or 15% better than someone. So you'll grow just 10 or 15% more compared to the other person, if you see the ideal condition. But if you invest more time, that 30-40% can go to somewhere like 60-70% more than someone else, who's good enough. So having said that, I would say that don't try to learn from those points in mind. Just start learning, and I'll try to keep all the applied stuffs side by side. So whenever you'll see a gradient, gradient is, by the way, the delta symbol, which is upside down, or a curl or a divergent or any other thing in mathematical physics, you'll try to relate it with the practical use of it, or why that gradient sign or curl sign is important, or what does it mean. And with that meaning in your mind, you'll probably understand stuffs better. For example, during our school days or college days, early college days, we all learn differentiation and integration. But how many of us practically know why differentiation or integration is used? What is the use? Why should we learn integration? Here in this PDF file, you see a lot of equations: area of the curve and sine A, sine H. And if you go down, you'll see integrations. But what is the physical use, or you can say in general theory or in layman's language, what does integration mean? So if you start asking that question, many of you probably would not be able to answer. It's not because integration is advanced stuff. It's because many classes or tutors or online courses or textbook do not answer those stuffs, or even if they answer with a very strong and small way. It's briefly explained, and you do not have enough time to understand why integration is being used and in what scenario it is being used. So after 5 years, when you go to your workplace, where you have to measure how much water is flowing through a tube, you find it difficult, because what you will do, you will try to find out the area of the tube, and then you'll try to do some manual calculation. And if the area is not regular, if the flow is not regular, you'll probably not know how to find out what was the amount of water that was flown in, say, 10 minutes. Had you learned integration or derivative during your college days with the practical knowledge of where I can use it? You could have probably used this integration thing there in case of flow of water, and you would have arrived to a pretty good result. So it's easier said than done. So I believe that after 10 years of experience, many of us will know what they actually want to know during in their career, because with this much of work experience, you know what are your stuffs, where you are good at, and what you will be doing for next 10 or 20 or 50 years. So if you are 10 or 15 years into your career, you will probably do not want to learn new stuffs, because you know those are not your cup of tea. But believe me, if you keep on learning stuffs till your retirement, you will be growing till your retirement and years to come. So what I believe, that everyone should start focusing on their weak points and start learning. In this short channel which just means started, I have had something in my mind since probably 2010 or so. So I wanted to begin some online classes and teach people how to deal with stuffs. The stuffs those are tough, or those are ignored sometimes. But due to my schedule and due to my other commitments, I was not able to give enough time. So today, when I was sitting and having a cup of tea with my wife, I thought that I'll start now. And as soon as I thought, I tried to find out what is the best medium to teach people. There are plenty, believe me, there are plenty of ways by which you can start doing what you want, and that I found in this teaching way also. But then I thought YouTube is something where you can start with a good amount of students actually going to YouTube and searching for their stuffs, what they want to learn. And I'll try keeping new videos and keeping live classes every day, or at least 2-3 times a week. And I'll try to go through the complete mathematical physics step by step. And I'll encourage each and every one of you to follow my channel, and probably you can write your comments in the channel, so that I can answer them. And if you have some stuffs or questions or queries out of out of the syllabus or out of the discussion, you could still probably write those stuffs in the comment, and I'll try my best to answer them. And I'll try to answer them as quick as possible, because as of now I've tried or I've committed to give few hours a day to teaching stuffs. So I'll probably have enough time to answer your questions. And I hope the class that I've begun and the motive behind teaching mathematical physics is will give you some I'll not say you'll completely understand mathematical physics, or you'll be a champion of mathematical physics in a day or two. It's a long run, and gradually you'd probably find that I'm going slower than you are learning, or I'm going faster than you're learning. You can always text me or write me or send a comment, and believe me, I'll try my best to keep everyone in the same page, because all I'm doing this thing is for the audience, for you guys to learn mathematical physics. and as soon as you start learning and then as soon as you learn those stuffs, probably the engineering, the science will be better, and it will help everyone. So with that in mind, I'll start my class, and I believe that I'll be able to start with a textbook, and I'll try to keep my all my classes short, so that anyone can begin a video offline, or they can come on my live classes with minimum disturbance to their regular schedule. If I keep the class for 2 hours, I know nobody will come, and it's not good for you guys, because I just want to deliver something which I have gained during last 15 years in my career. But if it is not been taken by others, by guys who are students, who are just beginners, who have just begun, or who are into their career and who are dealing with mathematical physics stuffs, then it will have of no use. So I'll try to keep my focus on the audience, and I'll try to keep things simpler. I'll not try to mess with too many equations or too many new stuffs. I'll go one by one. But if you find something interesting about my class, or if you have some questions, you please share them on the comment side. Thank you. So probably I'll start my class from every day, probably 7 p.m. Eastern Time Zone, and you can see the video later on whenever you have time. So I wish you all the best. Hi everyone. So in my previous class I have just introduced myself. I am Dr. Sunil Kedia, and I have been doing physics and related stuff since many years, and I've just created this mathematical physics channel to teach people about some of the fundamentals and basics of mathematical physics, and I'll definitely go to the advanced classes of mathematical physics once I cover all the basics. I would encourage everyone, each and every one of you, to go through the basic classes, because once we go to the advanced classes, it will be difficult for those who are not familiar with basic mathematical physics to grasp what is being taught. So I believe that it will be very good if you start or attend my classes online, or if you want to learn mathematical physics, and you can give some time during any time of the day, and you can see if I have posted a video, and you can go through that. So in this first class of mine, I'll introduce a book to you, though I would not say it's a Bible of mathematical physics, but it's a good book to start with. With time to time, I'll probably change the books, because all the books are not same, and some of the chapters or some of the discussions in one book is better than the other books. So I have plenty of mathematical physics books, and I'll probably change them as and when needed to discuss some certain topics. To start with, I have this book, you see, The Mathematical Methods for Physicists, a concise introduction, and it is written by Tai Cho. So it was a Cambridge University Press, and I found the beginning of this book very interesting. So it gives an idea of what a vector is, and how to do the tensor analysis. So of course vector can be quite easy stuffs to learn, and most of us might know what is a vector, so I'll not spend plenty of time in it. And as you go down in the content section, you'll see some of the vector differentiation, some operators, and how the operators are used, what the formula for using. This is, by the way, most used, one of the most used operator in mathematical physics. And what are the coordinate systems, what are the theorems. Means I would say that chapter 1 in this book is pretty concise, and we'll probably go through the some of the topics that should be taught in chapter 1 from other book. But for now we can probably refer to this book and begin our class. So let me go to chapter 1. You can probably download this book and go through the text once our discussion is over, so probably it will be faster for you to grasp. And after the video you can probably read the stuffs, and if you have some doubts you can write to me. So in chapter 1 we'll first start with the basic things like what is a vector and what is tensor analysis. This guy we are going to discuss later, this one, because we are not dealing with tensor analysis now. We'll be dealing with vectors. What is a vector and what is a scalar? Scalar is something that is like the opposite to vector, and though most of you know it, but for the sake of completeness I'll go through them, and I'll not go through reading this text, because I know you can very well read English. The point is, if you see a physical quantity like let us say if you have a block of metal, so it will have some mass, so it has a quantity called a mass, which is a scalar. Why scalar? Because mass can be represented as 20 kgs, so it has a magnitude, and 20 kg doesn't have a direction. So the quantities that we can represent in just magnitude and no direction. Here unit can be there intact with it, but no direction. You cannot you never say that the mass is 20 kg south, or the volume is 14 millimeter cube north. You do not represent these stuffs with a direction. You represent these stuffs with just a numeric value and the unit. So these quantities are known as scalars. So it's written here, like you can read it: a physical quantity that is completely specified in appropriate units by a single number, called its magnitude, such as volume, mass and temperature, is called a scalar. So my questions to you guys will be, I'll expect you all to answer it in my comment section, so that I'll know you guys are following me. Tell me one scalar quantity that is not mass, temperature or volume, because those three I have already told. Tell me a fourth scalar quantity that you are aware of. Scalar quantities are generally real numbers, and again it's kind of what is a real and imaginary number that we are going to learn later, but those are just numbers, you can say. And scalar quantities can be added like we do addition of algebraic functions, like added 5 kg plus 10 kg equal to 15 kg, 5 kg multiplied by 20 kg is equal to 100 kg square, and so on. So scalar quantities are they follow algebraic equations and they are commutative, means if you are adding 5 kgs with 10 kgs it gives you 15 kgs. If you are reversing the way of addition, say if you are adding 10 kgs to 5 kgs, it will again give you 15 kgs. So they are commutative. But what if your mass or your body is moving in a direction? So let's say you are driving a bike and you're driving with a speed of 60 miles per hour. Somebody calls you and you answer them that I am going at a speed of 60 miles per hour. So he might ask you that which direction or where you are heading. Means 60 miles per hour is good, but where you are heading, which direction, so that he'll know your position. So here the velocity or the movement of vehicle cannot be a scalar anymore. It has to be attached with a quantity called direction. So if you see this quantity A, it has some arrow sign on top of it. So that arrow sign represents this arrow sign. This represents the direction. Some of the stuffs which have directions are like velocity, I already mentioned. Force, if you are applying a force on something, so it will have a direction of force, because either you'll apply from top to bottom or bottom to top or left to right or right to left. It cannot be at a single point. So I introduced you with two quantities, the scalars and the vectors. In this textbook they have told that any italic letters are scalars and any letter written in bold are vectors. It is easy for them to write bold characters instead of writing an arrow on top of it. So in all textbooks you'll find bold characters as vectors and italic characters as scalars. So I'll go to one of the stuffs. Here you can we are reading as scalars and vectors. So this is our lesson today, and we have learned that a quantity A is scalar, but if you put A and if you draw an arrow on top of it, it will be a vector. So if you say this A and this one, how they are different from each other? So basically this has a property that this is same A plus a direction. If you say 60 miles per hour, it will be representing this A. But if you say 60 miles per hour towards north, so it will be representing A with a direction. So it will become vector, this will become scalar. So this arrow, of course you cannot write an arrow like this, nobody will understand. So we write such things as A is the scalar quantity, and if you write a cap on top of it, it's like just the direction. It's a unit vector towards north if you're going towards north, towards south if you're going towards south. So it has no numerical value, it just adds a direction to this guy. So if you write it like this, A is a vector quantity is equal to, you can represent it by A is a scalar quantity and A cap. A cap is the direction of this scalar quantity. So this will imply you that if you want to find out direction of a quantity, you simply take the vector and divide it by a numerical value of same quantity, or this can be written as the vector and you are taking the magnitude of this vector to make to get the numerical value. So basically you can write a cap is the directional unit vector towards the direction. Unit vector means its magnitude is 1, so whenever it is multiplied with a scalar quantity, it doesn't change its magnitude, its numerical value, it just adds direction towards the direction of this vector. So here you can write this equation as changing a to the magnitude of vector a as a vector divided by a vector's magnitude. So it's quite easy to represent the unit vector towards any other vector. So if you have a vector quantity a, I'll tell you how those things are done in mathematics. Don't worry about it. But if you have a mathematical quantity called a, and if you are trying to find out just the direction and not the magnitude, you can find out this way. You have a magnitude of this vector a, and you divide the vector by the magnitude and you'll find the direction. So it's as simple as that. Going back to the textbook, you see it's written the same thing. This is a vector because it is bold, and the bold a vector is equal to the magnitude of a into direction of a. But there are certain things that we should learn before we end today's class. Not all the quantities with a direction are vectors. Yes, but those who are vectors have a direction. So if you know that you have a vector quantity, you certainly know that it has a direction. But if you know that there is a quantity with a direction, you cannot say that it's a vector. It can be a vector because 99% or 95% of quantities with directions are vector, but not all. So how to decipher them? Just few minutes back I have told you one property called commutation. When you add 5 kgs to 10 kgs or 10 kgs to 5 kg, the result doesn't change. So that commutative property also applies to vectors. If you have a vector quantity and if you are doing adding two vector quantities or subtracting two vector quantities, they should be commutative, not subtraction. Subtraction cannot be commutative. Addition is commutative. So they have written it here very clearly. Not all quantities possessing magnitude and directions are vector. For example, angular displacement. Forget it, it's a very technical stuff. I'll tell you. If you are trying to move in a circle, so though you are moving and you have a direction, it's the perimeter of the circle, you cannot say that your movement is a vector. You'll say it as a scalar quantity, because every time, every moment your direction is changing. It's not fixed towards north or towards east or towards south. Since it is changing, it has a direction, but it is changing. So it cannot be a vector quantity. So here they have given one example. Let us say you have a block, and these are the three axes: the length, the thickness, and the width. So if you rotate this block 90 degree around z-axis, so if you rotate it around z-axis, if your thumb is towards x, towards z, and you rotate it, so you'll get something like this. This hole will go towards x axis, and y will be like this, because this is moving like this. And then if you rotate it about y axis, so it will fall flat like this, with the hole pointing towards z direction. So you have done two things: first you rotated about z axis and then about y axis. But if you do the reverse, first about y axis and then about z axis, the result is different. So these are not commutative, and since it is not commutative, the the movement of this block cannot be said to follow the vector calculus or vector quantity formalism. So in the next class we'll discuss how a vector is defined with its unit coordinates, unit direction vectors, and how they are identified as, how they are added, how they are subtracted, how they are multiplied, the vector addition, the vector subtraction. Those things are quite necessary for everyone to understand, because when you go to advanced mathematical physics problems, you might encounter some certain stuffs that you have to use such things like vector additions and subtractions. So it's good that we start from here and we progress. I'm already 20 minutes in this lecture, so I would guess I'll stop here, and in my next class I'll teach you how the vectors do work. For scalars it's quite easy. Since our childhood we are using scalar quantities, and we are adding them, we are subtracting them, we are multiplying them, and it's quite the normal way. But for vectors, the mathematics changes, the algebra changes, so we need to learn how to deal with these vector quantities. So in the next class we'll discuss those things. Till then, goodbye.